Welcome to the class of stochastic processes. Today we are going to talk about Markov chains. Markov chains is very useful probability tools for describing the behavior of a stochastic system. A stochastic process xt represents a collection of random variables associated with time. If t is a countable set, then we call this a discrete time process. If t is an interval of the real line, then we call this a continuous time process. We'll put it like xn is equal to I to represent the process at time n. The process is in state I. If the following property is satisfied, then we call xt is a Markov chain. This property, as will be described later, is called a Markovian property. And the Markovian property states if the conditional probability of xn plus 1 is equal to j, given xn is equal to I, and xn minus 1 is equal to in minus 1 up to xn x0 is equal to I0. If this conditional probability is equal to the conditional probability of xn plus 1 is equal to j, given xn is equal to I, then this is called Markovian property. So what that means is the conditional probability for the future state xn plus 1, given the present state xn is called the present state. And this xn minus 1 up to x0 is called the past state. So if the conditional probability of the future state xn plus 1 future state given the present state and the past state is equal to the conditional probability only given on the present state. In other words, that means the past state do not matter at all. And then this is called Markovian property. If a stochastic process satisfies the Markovian property, this stochastic process is called a Markov chain. So as we just described, this is called Markovian property. So that means the conditional distribution of any future state xn plus 1 given the past state and the present state. This is independent of the past state and only depends on the present state. Then this is called Markovian property. And if xt satisfies the Markovian property, then xt is called a Markov chain. So we let a Pij to represent the conditional probability xn plus 1 is equal to j, condition on xn is equal to I. So we use Pij to represent the probability that the process starts from I and next makes a transition into state j. So from xn to xn plus 1, we start from I, and the next step we go to j. And this Pij satisfies the following two properties. First, Pij is greater than or equal to 0. This is because Pij is conditional probability. Conditional probability is probability. So obviously, this Pij must be greater than or equal to 0. Number two, summation Pij must be 1. This is because we start from I. The next step will go to some state j. So if we sum over all possible state j, then that must be 1. The summation must be 1. And if we put all this Pij together into a matrix, then this is called P. This matrix is called one-step transition probability matrix. We give an example here. Suppose that the chance of rain tomorrow depends on previous weather conditions, only through whether or not it is raining today, and not on the past weather conditions. And suppose also that if it rains today, then it will rain tomorrow with probability alpha. And if it does not rain today, then it will rain tomorrow with probability beta. So if we use a Markov chain to represent this weather condition, then we can write the transition probability matrix P like if today is going to rain, then tomorrow the probability that it will rain is alpha, like this. And on the other hand, if today the weather condition is rain, then tomorrow it will not rain. Must be 1 minus alpha. Similarly, if today the weather condition is not rain, then tomorrow the weather condition is rain, will be beta, and not rain 1 minus beta. So this is a transition probability matrix. Chapman-Kolmogorov equations. So we have learned one-step transition probability matrix. We also have n-step transition probability matrix, P-I-J-N, that represent the probability that a process in state I will be in state J after n step. So P-I-J-N is equal to condition on the current state Sk is equal to I. And after n steps, additional n steps, so that's k plus n, or we can put it like n plus k. And what's the probability that xn plus k is equal to j? And this is called P-I-J-N. That means we start from I, and after n steps, we go to j. So clearly, P-I-J1 is equal to P-I-J, so we can just omit 1 here. So Chapman-Kolmogorov equations is to describe that P-I-J-N plus n is equal to summation P-I-K-N times P-K-J-M, and we sum over all possible k. So that means if we start from I, and after n plus m steps, we go to j, this probability will be equal to, we start from I, and after n step, at least we will go to some state k, right? And after m step, we start from k and go to j, and we sum over all possible state k. So this is called Chapman-Kolmogorov equations. Now we prove that P-I-J-N plus m, based on the definition, we know that means we start from I, and after n plus m steps, we go to j, right? And we are talking about the conditional probability here. And then we can put in one more condition. Xn is equal to k, and we sum over all possible k. And then we can write this equation to be like conditional probability xn plus n given xn and x0, and times conditional probability of xn given x0. And then because this is a Markov chain, so x0 does not matter. So we can just skip x0 is equal to I here. So xn is equal to k, and xn plus 1 is equal to j. Based on the notation we just learned, this is called pkj. And because this is n step, this is n plus m step, so we take extra m step here, right? So pkjn. And this is called pikn, because we are from 0 step to the nth step, right? So pikn. And we take summation over all possible k. And then we can swap these two probabilities. So we have pikn times pkjn. And we take summation. Now, if we let pn, notice that this p is a little bit different from this p, right? It looks very different. So because this p is used to represent a matrix, and specifically the matrix of n-step transition probability matrix, PIJN. So if we look at this equation, we know that this is simply the matrix multiplication equations, right? So we know Pn plus m. This matrix can be expressed as the matrix Pn and Pm. Notice that Pn plus m that represent n plus m step transition probability matrix, and this can be expressed as transition probability matrix P, n-step transition probability matrix times m-step transition probability matrix. So for example, P2 can be expressed as P1 plus 1. So that is P times P, so that's P squared. P squared means the matrix is multiplied itself twice, okay? And this is the two-step transition probability matrix. So that's different. But then we prove that the two-step transition probability matrix is equal to one-step transition probability matrix P to the square. Okay? And similarly, we can prove that the n-step transition probability matrix P, okay, Pn is equal to one-step transition probability matrix P to the power of n. Example. The weather is considered as a two-state Markov chain. If alpha is equal to 0.7 and beta is equal to 0.4, then calculate the probability that it will rain 4 days from today, given that it is raining today. So 4 days. So we are looking at the four-step transition probability matrix. And based on the one-step transition probability matrix, we have known that this is one-step transition probability matrix. So we know that the four-step transition probability matrix will be equal to one-step transition probability matrix to the power of 4. Okay? So that is, you kind of multiply this transition probability matrix 4 times. Okay? So that will be the result. So, but the problem is looking at the probability that it will rain today, and that it will rain 4 days later. So that is rain today and 4 days later. So we are looking at this value. Unconditional distribution of the state at time m. If we let alpha I represent probability of x0 is equal to I, and obviously summation alpha I must be 1. So probability xn is equal to j can be written as summation x0 is equal to I and times all possible, and times probability of xn0 is equal to I, and we sum over all possible I here. Okay, so based on the notation, this conditional probability is called Pij after n step, right, from 0 to n. So Pijn times this is alpha I. So for example, if you want to know what is the probability that x4 is equal to 0, then you could just use 0.4. This is, suppose that x0 is 0.4 and x1 is equal to 0.6. Then you could just use 0.4 times P004 plus 0.6 times P104, and you will get 0.57. Classification of states. State J is said to be accessible from state I if Pij is greater than 0. So that means it is possible that we start from I, and after some steps n, we can go to j. So if Pijn is greater than 0, then we call j is accessible from state I. Note that this implies that state j is accessible from state I if only if starting in I, it is possible that the process will ever into state J. And this is because if J is not accessible, so we use the argument like what follows. If J is not accessible from I, then we know that the process is in state I, then the process will ever enter state J. This probability is equal to will ever enter state J. That means for some step N, the process will enter state J. So we take union here. Okay? And probability of union will be less than or equal to summation of the probability of each event, right? And we know that this is Pij0. So if this is Pijn. So if Pijn is 0, then the summation of Pijn must be 0 too, right? So we know that if the process is not, if J is not accessible from I, then that means the conditional probability that stay in I, stay in I, then the process will ever enter J must be 0. Communicate. If two states I and J, if we say these two states communicate with each other, that means the process can start from I and go to J, or the other way around, start from J can go back to I. And we have the following four properties. First, Pii0 must be 1. This is a conventional, this is by convention. So that means we start from I, then we will, the x0 will be I, the probability of x0 will be I, will be 1. This is by convention. That means we assume that any state will communicate with itself. And the second property is that I will communicate with itself, I, of course, and I will communicate with J, then J will communicate with I. Or if I communicate with J, J communicate with K, then I communicate with K. Also, if I communicate with J, then IJ are said to be in the same class. And two classes are either identical or disjoint. So if we say some states are in the same class, that means all the states in the same class can communicate with all the states in the same class. Okay? And a Markov chain is said to be reducible if there is only one class. So that means all states communicate with each other. So we give an example here. So consider Markov chain consisting of the three states 0, 1, 2, and having transition probability matrix as follows. So this is state 0, 1, 2. This is state 0, 1, 2. So let's look at here. So from 0 to 0, there's a positive probability that can go from 0 to 0, right? So 0 can go back to 0. And 0 can go to 1, right? So 0 can go to 1, like this. And 1 can go to 0, so this the other way around, right? And 1 can go back to itself, so 1 can go back to 1. And 1 can go to 2. Then 2 can go to 1. And the 2 can go to 2, right? So let's look at this. So 0 and 1 communicate with itself, right? Because you can go to 1 and 1 can go to 0. And 1 can go to 2, 2 can go to 1. So all of this 0, 1, 2 belong to the same class. Another example, so consider Markov chain 0, 1, 2, 3, and this is the transition probability matrix. So based on the approach we just used, you can put a diagram like this, and then you can classify all the states. For example, because 0 and 1 communicate with each other, right? So that belongs to the same state. But then, how about 1 and 2? 2 can go to 1, but there is no way that 1 can go to 2. Okay? So 2 and 1 do not belong to the same class. And similarly, 2 can go to 3, but 3 cannot go to 2, right? So 2 and 3 do not belong to the same class. So turns out that 0 and 1 belong to the same class, and 2 belongs to one class itself, and 3 belongs to one class itself. Classification of states. Let Fi denote the probability that starting in I, the process will ever re-enter state I. So if Fi is equal to 1, then we call I, the state I, we call I recurrent. That means that will happen again and again. On the other hand, if Fi is less than 1, then we call I transient. Transient means after a long time, eventually we will not go to J. If after a sufficiently long time. Okay? So if I is recurrent, that means I will go to I eventually and go to I and go to I. So that means I will be visited infinitely often. If I is transient, then the probability that never again visit I will be 1 minus Fi, because Fi represents the probability that the process will ever re-enter state I. So the probability that it will never again visit I is 1 minus Fi. And because I is transient, so Fi must be less than 1. So 1 minus Fi will be greater than 0. So let's look at this. So probability that the process will be in state I for exactly n times, that will be Fi to the power of n minus 1 times 1 minus Fi. Because we start from I, and then the process will be in state I for exactly n times. So that's Fi to, should be Fi. So exactly n times, so that's Fi to the power of n minus 1. And times something, some state, for example, J, that is not I. So if you want to go from I to some state, that is the probability is 1 minus Fi, right? So you have Fi, n minus 1, the power of n minus 1 times 1 minus Fi. And we can observe the following two properties. Summation Fi to the power of n minus 1 times 1 minus Fi, that must be less than infinity. Okay, so by Fourier concatenated lemma 1, which we learned in previous lecture, we know that probability that the process will be in state I infinitely often will be 0. And also n, that represent the number of times that the process will visit I, is follows geometric distribution with the probability 1 minus Fi. So you can look at 1 minus Fi as a probability of success. Here we can define success as the state will go to, the process will go to some state that is not I, right? So we know based on the knowledge of our knowledge about geometric distribution, we know that the expectation of n must be 1 over 1 minus Fi, and that must be less than infinity. So that means if I is a transient state, the expected number of times that the process will be in state n will less than infinity. On the other hand, if the state is recurrent, as we have learned that the number of times that the process will visit the state will be infinite. Okay? So, if I is recurrent, if and only if, starting from state I, the expected number of time periods that the process is in state I is infinite. And specifically, we can use if if we let an indicator function in which is 1 or 0. If the process is in state I, we put it like 1. If Xn is not equal to I, we put it 0. And if we want to count the number of times the process enter state I, then we are actually calculating expectation of summation in given x0 is equal to I, meaning we start from I, right? So, and based on the knowledge about expectation, we can move summation outside the expectation. So we have this. And we know that this is actually the expectation of in given x0 is equal to I. This is actually the conditional probability of this. And this is actually PIIN. Then we take summation. And because if I is recurrent, we know PIIN must be some constant greater than 0. So summation of one constant that is greater than 0 must be infinity. Right? So we know that the expected number of times that the process in state I will be infinite. Proposition: state I is recurrent if summation PIIN is infinity. State I is transient if summation PIIN is less than infinity. So in the finite state Markov chain, not all states are transient. Because if all states are transient, then the process has no place to go, right? Okay. And also transient and recurrent is a class property, meaning all states in one class are either all transient or all recurrent. Corollary: if I is recurrent, then I and J communicate with each other, then we know that J is recurrent. Why is that? We prove this as follows. If I and J communicate each other, that means there exists some number K and M such that Pijk greater than 0 and Pjim greater than 0. So for any integer n, Pjm plus n plus k, this is greater than or equal to Pjim, Piin, and Pijk. Why is that? Because Pjm plus n plus k, that means we start from j after n plus n plus k steps, we go to j. And this is simply one possibility, right? We start from j, and after n step we go to I, and after n step we stay in I, and after k step we go back to j. This is simply one possibility. So the probability of this is greater than or equal to this probability. So if we take summation on both sides, we take summation like this. And so this is the left-hand side, and we take summation. And because we take summation, this is about n, right? So Pjim and Pijk, we can move them outside of the summation because they have nothing to do with n. And Piin, we know that because I is recurrent, so Piin must be infinity. So overall, the right-hand side is infinity. So the left-hand side must be infinity. So we know that J is recurrent. Example. So we have a one-step transition probability matrix here, and we can draw the diagram like this. And as we learn that how can we classify the state? 0, 1, 2, 3. All of them belong to the same class. Why is that? You can check. So can 0 go to 1? You can check. Yes. How can 0 go to 1? Because 0 go to 2 and 2 go to 1, so 0 can go to 1, right? So 0 and 1 belong to the same class. And can 0 go to 2? Yes, obviously. Can 2 go to 0? Yes, because 2 can go to 1 and 1 can go to 0. So 0, 1, 2 belong to the same class. How about 2 and 3? Can Can state 2 go to state 3? Yes. Why is that? Because 2 can go to 1, 1 can go to 0, 0 can go to 3, so 2 can go to 3, right? And can 3 can go to 0? Can 3 go to 2? Yes, because 3 can go to 1, 1 go to 0, and 0 go to 2. So all of 0, 1, 2, 3 belong to the same class. And because this is a finite Markov chain, and we have said, if this is a finite Markov chain, all state, there must be one state that is not transient. And because they belong to the same class, and the recurrent and the transient is a class property. If we have at least one state that is recurrent, and then all the states must be recurrent, right? So all the states are recurrent. And similarly, and this is another example, you can classify all the states. And then it turns out that 0, 1, 2, 3, 4, we have 3 states. We have 3 classes. And we can check 0 and 1 are actually recurrent, and 2 and 3 are recurrent, but 4 is transient.